Hey guys, what's up? Eddie Alho here with KissAnalog.com. Hey, today we have a Class D amplifier and we want to power it, right? So this is going to be the video where we power it with a switching power supply. Okay, this is a 600 watt power supply, 600 watt Class D amp. So let's see how the two things work together. Alright, what we'll do first is we'll power this up, and we're going to open it up later, look inside too, but let's power this thing up and look at the noise coming out of it. And then when we connect it to the Class D amp, there's always a little filtering at the input. So hopefully whatever noise we see coming out of this will be filtered when we connect it here, okay? And then finally, what noise can get through the amplifier? Now, it's called power supply rejection ratio, is the ratio of how much noise is at the input versus what we see at the output. So let's try that, okay? And yeah, let's see what happens. Because it makes sense to power a switching amplifier with a switching power supply, right? Keep everything light, efficient, all that good stuff. So yeah, this is a big question. I've been looking forward to this video, so let's jump into it. Hey, and by the way, yeah, there's some craziness going on in the world. I hope you guys aren't affected by it. I'm sure some of you guys are, and I'm sorry about that. It really sucks. And yeah, hopefully, man, things will get back to normal before they get worse, right? So, but in the meantime, if you guys can, we can watch a video and try to not think about what's going on outside, right? Okay, so here at the bench, I'm safe, right? Let's go on with the video. Alright, so our power supply's in the box. Just before we open that, I'll just go over the board real quick for those who haven't seen the last video. Our input 48 volt connector right here. It comes to a switching regulator, gives us 12 volts, and a linear that gives us 3.3 down here. Then we have our inputs right here, and our outputs here, right and left. Okay? So our input op amps and filtering circuit, and under here is our TPA3255. Then we have our bulk capacitors, 4,700 microfarads each, and our LC filters for each output. Okay, and really nothing on the back of the board. Okay, so let's go ahead and open up our box, our power supply. Alright, there's our power supply. Caution, high voltage, 48 volt with some serial number, I think. Okay, there's the label there, 600 watt, 48 volts. And then on the other side of the power supply, our 110, 220 volt switch. And it's funny, 110, 115 on the thing, but actually our US power is 120. Alright, and then on our input power side, we got our plus V, our minus V. So we have 3 terminals for plus V, 3 for minus V, and then 1 for our safety ground symbol there, and then neutral and line, so neutral and line. Okay, so then ground, neutral, and line. Then on this side it says an adjust. So I'm actually going to see if I can adjust this up to maybe 50 volts, get a little more power. Okay, so regarding cooling, which is always an important thing with power supplies, here's our fan, of course, and I'm guessing this is probably pushing air out the top, and so it would be sucking air through these vents across the power supply. There's these vents right here, but really there's a vent across here that is going to pull air across the front of the power supply here, and then also along the edges, so it'll pull air across the bottom along the edges out the top. So yeah, we'll see how that works. Alright, so what I have is I have the power plug right here, ground, neutral, hot, or line, and then I have the output. I have a resistor here, 8 ohms, so 48 volts, we should get some power. And I've got the Bryman EEV blog meter connected to the output so we can watch the output come up. I'm going to bring the input up slow, so maybe I'll put another meter. Alright, I added another meter. So I've got the Klein Tools meter on the AC input. So you'll see this come up slowly. At some point we'll see the output pop up. Okay? Hopefully everything works. Let's try it. I'll be using my B&K AC power supply to bring up the voltage slowly. Okay, so it starts off with 1.3 volts. Let's go ahead and bring it up. Alright, so I had this on AC, that's why we didn't see any voltage. So cockpit air, get that on DC. And you might have saw the LED start coming on when the power came up. So that's kind of cool. And okay, let's do it again. Okay, so you might have seen the light blinking. Since we were coming up into load, as the output tries to come up, it's trying to supply a bunch of current. And so at that low input voltage, you saw it kind of bounce on and off. Alright guys, so that was a little bit too much power for my B&K power supply. So I put two 8 ohms in series, 16 ohms. So that's still going to be about 150 watts roughly. So let's go ahead and power it up again. Okay, so I don't know if you could hear the fan. It wasn't too bad, but it was a little fan noise. Now, I don't know, maybe if I power it up with no load, if the fan's going to kick on. But with about 3 amp load, the power does kick on the fan. Okay, so before, with the 8 ohm load, we had about 288 watts. And now we have about 144 watts. And it seems to work. Okay, so let me go ahead. And this time, instead of bringing it up slow, I've got it set for about 120 volts. Let's go ahead and just hit the switch. Okay, so if you're listening for the fan noise, you can see, you can listen for it to see how loud you think it is. I'm going to go ahead and adjust this. I'm going to try to adjust it for 50 volts. Okay, 49.4 volts is as high as I can go. One more check, see if it powers up with that setting that I just did. Yeah, about 49.4. Alright, so now we're ready to run a test. I've got my differential probe from the Pentec, the DP25. It's in the X20 scale. So we're going to bring up the voltage and we're going to see what kind of noise we have right here going into our 16 ohms, okay? Right around 150 watts. And let's just see what it looks like. So we'll be looking at the spectrum on the Mix 6 scope. Right up here. Alright, so what I have is, I'm coming in channel 2. So it's 20 millivolts per division. It's AC coupled. And then we have our math, our FFT right here, okay? So you can see right now, that's just a noise floor right there. And I've also got this measurement down here. We got 60 millivolts peak to peak and 4.6 millivolts RMS. So yeah, we're under 5 millivolts RMS. Alright, so there's what it looks like. And let's go ahead and power it up and see what happens. Now one thing just to mention is when I am in the FFT, it's 100K per division, okay? And the reason I said it that way is a lot of power supplies switch around 100 kilohertz, 200 kilohertz, so we should see a spike right around 100K or where the switching frequency is, and then a harmonics from that, okay? And then any other kind of ripple noises. Alright, I'm going to go ahead and power it up. And there we go. Okay, here, let me just freeze that. Now, you can hear the fan down here. Here, I'm going to move the microphone right over here, but real close to the fan. That's the fan noise. The B&K also makes a little noise, the AC power supply, but I'll shut up so you can hear the fan. Okay, that's the microphone placed close to the fan. Alright. Alright, and incidentally, I've got the power supply right here. I can feel the air blowing out this way as we suspected. And that's how I was getting the microphone close to it so you can hear the fan right up close. Okay. Alright, let's go back to the scope. Okay, I'll turn off the power supply so we have some quiet here. From the B&K makes a little bit of a humming noise, but I had the microphone next to it, so that's why it came out so loud. Alright, so first what I'm going to do is I'm going to hit the zoom button. And see the little window right there? That's what we're zooming into right here. And what I wanted to show is, let's see, this is 100 kilohertz, but if I go to channel 2, it'll say 10 microseconds per division. And so we're about a division and a half. So it's, well, here, let me get the cursors over here. Get that cursor. Where's the other one? Alright, it's about 80 kilohertz. So that sounds about right. 80 kilohertz switching. And then, so you can kind of see the ripple. Remember, this 20 millivolts per division. And our zero line's right here. So we're getting about 40 millivolts peak. And maybe 20, 40. And then we got these little longer peaks, but you know, that could be also some probe pickup, some noise, some extra noise from the probe. But yeah, that looks about right. I mean, it's not too bad. Now, this is just going into resistive load. Once we go into our amplifier, we'll look at that too. Because what I'm hoping is the capacitive input board down here, when we go into our board right here, what I'm hoping is capacitors at the input will help filter some of that noise. Okay? So our load will essentially help filter us. Okay, so here, let's go ahead and turn off the zoom so we can, and then I'm going to turn off the channel so we can see our spectrum. Let me zoom in on that. Okay, so you can see all these spikes. I'll take one of these guys and put it on this first one, and that's 80 kilohertz, just like we saw. So see, there's another proof that our switching frequency is 80 kilohertz. And then I'll put this guy here, and it should be 160. And you know, it says 156 because I don't have it perfectly on there, but it should be a harmonic. If you can see that right there on the scope. Alright, so coming back over here, so you can see that they're 80 kilohertz apart. And then they kind of die away out here. So remember, this is 100 kilohertz, 2, 3, 4, 5, 6, 7, 8. So around a megahertz, really kind of drops off a little bit. Okay, so now let's go ahead and zoom in a little bit on this. Okay. Okay, so try to get that set up right there. So it's 20 kilohertz per 20, 40, 60, 80. Now I could probably put that right and have it exactly on the I can fine tune that. So, and then I can put the cursor here just to prove it to us. Put that right on the point, as close as I can, I guess. And 80 kilohertz. So there we go. And that'll be 160 and then 240. But yeah, that's the noise. Now, as far as amplitude, it's 20, 40. So it's minus 40. And it's a little bit lower than that. Here I can get the other cursors. And that says about 43 dB. So it's down 43 dB. Now remember, every 20 dB is a 10x. So 0 dB would be 1 volt. So that'd be 100 millivolts, 10 millivolts. So that sounds about right. Alright, so now let's move the differential probes from the power supply to the Class D amp. And we'll move the alright guys, okay, so now what we're going to do is move the power. Instead of going to the resistors, we'll go into the Class D amp now, and we'll look at the distortion, or we'll look at the the noise going into the Class D. What I think is going to happen is there's some filtering at the input of the Class D that will help filter the noise coming out of this. So let's see what that does. But then again, the Class D is going to start running, and it's switching, right? 400 and something kilohertz probably. So we might see some noise from that. But let's give it a try. Okay, so let me go over this new setup. Now I have the power supply, this cable right here, going to the input of the power, okay? And we've got our differential probes here instead of here now. So we're going to see if connecting it here, if the input capacitors help take away some of that noise. And then I've got the 8 ohm speakers, one tied to each output. Right now there's no signal going on the input. We're just going to, so there really shouldn't be any signal out here. But anyway, we're going to just see what the power looks like, just connected to that. There'll be a little bit of power that the board's going to be taking just to bring the chips up and run, even though there's no signal going out. Maybe a few watts or something like that. Let's just check the noise right here, okay? And by the way, the Klein is still looking at the AC input, and the Bryman is now plugged right here into the output as well. And there's our Pintec differential probe and our mixed signaler here, which we'll see in just a moment. Alrighty, I'm going to flip the on switch. And we get a couple red lights over here. We got 49.4 volts going in and about 128. That's a little bit high. I'm going to drop it down. It's pretty sensitive here, the knob. Just getting right, just under 120, I guess. Alright, that's good. But we have 49.4 there. Now let's go up and look at the scope. Alright, so there's channel 2. We got about 80 millivolts up, about 80 millivolts down, and some of this stuff on top still even. So here, let's just turn that off so we can see our FFT. And there we go, there's the FFT. Now it looks better before 80 kilohertz, right above the 40 dB, 30 something dBs we saw a spike, and every 80 kilohertz, right? And then it kind of rolled off out here somewhere. So now we have one that's up high, and we've got a bunch more out here that we didn't have before. And we've got more spikes than just every 80 kilohertz. That's probably the Class D amplifier running as well. But it did drop the spikes from the 80 kilohertz harmonics across here. Now, let's go ahead and zoom in at 20 kilohertz per, like we did before. Alright, so if I move this guy over to that first spike, it looks like it's about 50 kilohertz right there. So that's interesting. And then move this one over here. And that's almost 80, so that's our power supply. So that is our switching frequency. But now we have some 50 kilohertz stuff. So I think we've got some 50 from the Class D amp probably, I guess. Maybe subharmonics. I would think it's switching a lot faster. So it's just interesting how it's pushed it down, but we have spikes at different frequencies now. And this is 60 dB right here. So if that's 1 volt, that'd be 100 millivolts, 10 millivolts, and 1 millivolt right across here. So just above 1 millivolt. I'll zoom in on that so you can see a little closer. And there's a close-up shot. Alright, so now in the test what we're going to do is move the differential probes from the input to the output. And let's see if that noise gets through the Class D amplifier. I think it's going to reject most of it. So let's test it out. Alright, so we're running again. I hit the save button so we're live again. Okay, now here's our setup once more. And this time I've moved the differential probes to the output. So without any signal, let's just see what kind of ambient noise we have. I'll zoom in on this. Alright, so I've zoomed in on the scope. Let's go ahead and flip on the power. Alright, and that's what our output looks like with no signal. So that here, I'm going to go ahead and freeze it. See, there's our, here, let's drop that. So that's 200 millivolts per division, it looks like we have more noise, right? But when I freeze it and turn that off, the FFT shows less. So that's interesting, right? Here, let's go to get some more bandwidth again. 100K per. And yeah, we got a big old spike. So it looks like a lot of that noise is right there at that frequency, which is, oh, I'm not right on it. It's 440. So that's the Class D amplifier switching. So yeah, we expect to see that, right? But here, I'll freeze that. All right, so this noise is from the Class D amp, and it's at 452 kilohertz. So that's where all that noise is coming from. But look how 20, 40, 60 dB. So a lot of those spikes are not showing up on the output. We're getting this thing from the switching frequency. So if I go back to 20 kilohertz, at 20, this is 20 kilohertz per division. So 20K is right here. So that's actually our audible range right there, that first grid. So we don't see any noise, so it looks much cleaner, the output, right? So here, if I go down to, say, 5K per division, so that's 5K per grid. So 5, 10, 15, 20, that's out to 20 kilohertz right there. That looks pretty darn clean when you look at it that way, right? So if we said this is 1 volt, and then 100 millivolts, 10 millivolts, 1 millivolt, this is like 1/10 of a millivolt. Here, let me pop up channel 2 again, and let's zoom in on that. There we go. There is a frequency for the Class D amp. That's just the Class D running. So if we get these these cursors lined up, that's 458.7 kilohertz. So yeah, that's just a Class D amp, and this is 200 millivolts per, so it's 2, 4, 6. You know, it's, well, we can see it right here, 487 millivolts RMS and 1.4 volts peak to peak, and that's out of 450 kilohertz, which you can't hear that. So in the audible range, things look pretty clean. Okay, guys, I took out some screws, 2 screws on either side of this right here. These screws here, and I just want to pop this off. Not sure if it's just the tape there that's holding it. Let's see. Oh, we got 2 more screws on the end. Okay, there we go. Alright, there's our fan. Looks like it's glued down the connectors. I'm going to leave that. Kind of like that. Wow, there we go. There's our input. Here, let's zoom in. Alright, so I'll just point here. This is our EMI capacitors, our fuse. These are NTCs, it looks like, for inrush current protection. Our X capacitor, common mode choke, X capacitor, and here's some Y capacitors down here for to work with our common mode choke for common mode filtering, and then our bridge rectifier on a heat sink. So nice touch. That's our EMI filter up to our bridge rectifier, and then our volt capacitors. And this is the switch to switch these in depending on which voltage system we're on. Okay, then it looks like there's a little flyback converter maybe for some housekeeping voltages. And then we have our, and it's hard to say what this could be. This could be an LLC converter, so kind of a series resonant converter, because it looks like this could be the resonant inductor. And then our output capacitors, and these are our, I'm thinking these are our switching transistors. So one could be a switching transistor and the other one could be an output rectifier, but not sure. And we got a control chip down here. And then our feedback, you know, we have our pot here. There's got to be an opto coupler somewhere, and it could be down underneath here. This looks like a thermo feedback off of the heatsink here, coming back to here to control the input. As I try to move these wires out of the way, it looks like 2 opto couplers here. So we got feedback through, it looks like 2 of them. I'm not sure, you know, one's for voltage feedback, and not sure what the other one would be used for. And then here's a Y capacitor between secondary side and primary side. Sometimes that helps for combo noise. Now it's interesting, right down here it says PTA 500, it looks like 500 watt version 3. So this is supposed to be a 600 watt power supply. Maybe they're just pushing 500, 600 watts. And then the date is 2020 08 25. So it's a pretty recent build, it looks like. Looks like a pretty clean design, I think. Pretty clean manufactured. Yeah, I mean, I don't see any problems with this. You know, what I don't see though on this, as I look at it close, we have our LC filter and a little ceramic capacitor right down there between the plus and minus output. So what I think is you could probably tie into some of these terminals a nice poly cap, maybe a nice big ceramic, but probably a nice poly cap to help filter the output from here. So I think maybe I'd try that. Hey guys, so what do you think? It looks pretty good, huh? It looks like the power supply noise is being filtered pretty good at the input of the Class D amp. And certainly it looks like the power supply rejection of the amplifier of the Class D amp is rejecting a lot of that power supply noise from getting to the output signal. So in the next video what we'll do is we'll put a signal in, take it to full power, and see once this thing gets up to high power if we have any added noise. So we'll try that. And maybe what we'll do is we'll put a filter capacitor on these lugs here on the output of this guy, and maybe also over here on the Class D amp on the input of those terminals. I mean, they're big enough to crank down a capacitor, so yeah, maybe we'll try that too. Alright guys, so hope you liked the video. 2 thumbs up to my Patreons. Thanks for all your support. Appreciate you guys. And you become a Patreon for as low as $1 a month. Throw that out there. Appreciate all you guys watching the videos and the support. And thumbs up the video. A like on the video really helps YouTube analytics, helps the channel. A free way to help the channel, right? And by the way, I'll have links down below for these items I'm testing, and in case you want to build this up yourself. Okay? And that also is a free way to help the channel. It doesn't cost you anything extra. So appreciate you guys, and we'll see you next time.